Welcome, software engineers and IT enthusiasts. Have you ever felt trapped in dependency hell? We've all been there, chasing down outdated libraries, battling security vulnerabilities, and wrestling with compatibility nightmares. In the fast-paced world of Java development, managing dependencies is not just a chore, it's a constant, critical challenge. Projects quickly accumulate numerous libraries, each with its own lifecycle, potential vulnerabilities, and evolving versions. Manual dependency management is not only time-consuming but also incredibly error-prone, opening doors to security breaches, frustrating build failures, and subtle runtime compatibility issues that can cripple an application. Today, we're going to revolutionize how you think about dependency management. We're diving deep into AI DepGuard, an innovative approach that integrates AI-based intelligence directly into your CI/CD pipeline. AI DepGuard is designed to automate the detection of outdated and vulnerable dependencies, recommend optimal upgrades, and even auto-apply fixes, ensuring your Java applications remain secure, stable, and cutting-edge. Imagine a world where your dependencies are always in check, proactively updated, and vulnerabilities are squashed before they even become a threat. That's the power of AI-driven dependency management, and we're about to show you how to build it. Let's break down the core concepts that make AI DepGuard so powerful. First, we have automated dependency scanning. This is where your CI/CD pipeline regularly scans your project's dependencies, typically by parsing your pom.xml file in a Maven project, or build.gradle for Gradle. This initial scan creates a comprehensive list of all direct and transitive libraries your application relies on. It's the foundational step, providing the raw data that our intelligent system needs to begin its work. Think of it as taking an inventory of every single component in your software supply chain. Next, this raw dependency data feeds into the heart of our system, AI-powered analysis. While a full-fledged GenAI model might be overkill for every use case, our example demonstrates this capability using a sophisticated Python script that simulates a GenAI component. This script performs critical analyses, vulnerability analysis, checking identified dependencies against a mock vulnerability database to flag known CVEs, upgrade recommendations, intelligently suggesting the latest stable or secure versions for outdated libraries, and compatibility checks, which, though simulated in our example, can infer potential conflicts or breaking changes based on historical data or predefined rules. This analytical brain is what truly elevates dependency management from a manual chore to an intelligent, predictive process. Once the AI-powered analysis is complete, AI DepGuard generates actionable insights. The AI component outputs structured recommendations in an easily parsable format, like JSON. These recommendations aren't just generic warnings, they specify exactly which dependency needs attention, its current state, the recommended action, upgrade, fix, etc., and the precise version to move to. But AI DepGuard goes a step further with automated remediation. Based on these smart recommendations, another script can automatically modify your project files, specifically your pom.xml for Java Maven projects, to apply the recommended upgrades or fixes. This means less manual intervention, fewer human errors, and a significantly faster response to security and stability concerns. It's like having an expert developer constantly watching over your dependencies and fixing issues instantly. All these steps, from scanning to analysis to automated fixing, are seamlessly orchestrated within your existing CI/CD pipeline. This CI/CD integration transforms dependency management from an isolated, reactive task into an integral, proactive part of your DevOps workflow. Imagine every code push, every pull request, automatically triggering a comprehensive dependency health check and, if necessary, an automated fix. This not only dramatically improves your development velocity but also ensures your applications maintain a robust security posture by addressing issues before they become critical. It's continuous delivery, with continuous security and stability baked right in. Let's take a closer look at the AI DepGuard project structure itself. At its root, you'll find the .github/workflows directory, containing cicd.yml, which defines our GitHub Actions pipeline. The src/main/java path holds a simple app.java, a sample Java application that leverages some common libraries. The magic truly happens in the scripts/directory, home to AI_dependency_advisor.py, our Python script simulating the GenAI analysis, and apply_fixes.sh, the shell script responsible for applying recommended changes. Crucially, security/vulnerability_db.json acts as our mock vulnerability database, providing the AI with its knowledge base. And, of course, the pom.xml is our Maven project file, intentionally configured with sample dependencies, some of which are outdated or vulnerable for demonstration purposes. This setup allows us to simulate real-world scenarios effectively. Now, let's peek under the hood at the AI brain of our operation, the AI_dependency_advisor.py script. This Python script takes the verbose output of MVN dependency tree as its input. It then meticulously parses this output to extract the group ID, artifact ID, and version for each dependency. Once identified, it consults our local security/vulnerability_db.json file. This JSON file serves as our mock knowledge base, containing entries for known vulnerabilities associated with specific dependency versions. For example, it will flag an older Commons Collections 4 version. If a vulnerability is found, the script suggests a fixed_version from the database. Beyond just vulnerabilities, it also identifies dependencies that are simply outdated by comparing their current version with a hard-coded, latest stable version. In a real scenario, this would query Maven Central or similar repositories. Finally, it outputs a structured JSON report detailing the status and recommended actions for each dependency, laying out a clear plan for remediation. Following the analysis, the apply_fixes.sh script takes center stage as our autofix bot. This shell script reads the JSON recommendations generated by AI_dependency_advisor.py. Its primary tool for manipulation is smallstarlet, a command-line XML toolkit. Smallstarlet enables the script to programmatically update the pom.xml file, precisely changing the versions of dependencies as recommended by the AI. For instance, if Commons Collections 4 version 4.0 is flagged as vulnerable, apply_fixes.sh will update it to 4.4 in the pom.xml. After applying these changes, the script then uses Git to commit these modifications back to the repository. This automated commit is a critical step, ensuring that the changes are persisted and can trigger a fresh build to validate the fixes. It's truly a hands-off approach to keeping your project's dependencies healthy. Let's trace the journey through the cicd.yml pipeline in GitHub Actions, which orchestrates this entire process. The pipeline starts with a build job, which simply checks out the code, sets up JDK 11, and performs a mvn clean install to ensure the project compiles and all current dependencies are downloaded. Once the build is successful, the dependency_scan_n_recommend job kicks in. This job sets up Python, installs necessary libraries like Beautiful Soup 4 and LXML, then generates the Maven dependency tree and pipes its output directly into our AI_dependency_advisor.py script. The resulting recommendations.json file is then uploaded as a workflow artifact, and a crucial output flag recommendations_found is set to true if any upgrade actions are identified.